Hello students. Now finally we are going to discuss few exercises based on radiation sources. So the first exercise is this: which has the higher energy, a conversion electron from the L shell or from the M shell, if both arise from the same nuclear excitation energy. So there are two conversion electrons coming out, one from the L shell and one from the M shell, and the nuclear excitation energy is the same for both. So which one has got the higher energy? Since the energy of the conversion electron is given by this expression, which we have discussed in the third subheading when we talked about electron sources. So in that case, energy of the electron that is coming out is equal to the excitation energy minus the binding energy. So the binding energy of the L shell electron is more than the M shell electron, because L shell is closer to the nucleus and so it is more tightly bound compared to M shell, which is further away from the nucleus. So from the above expression, the conversion energy is more for the M shell electron, since the nuclear excitation energy is the same for both the processes. So the binding energy is less for M shell compared to L shell. So this particular quantity becomes higher for the M shell compared to the L shell. Now let us do another exercise. What is the lowest wavelength limit of the X-ray emitted by a tube operating at a potential of 195 keV? So the lowest wavelength that comes out when a potential difference of 195 keV is used to accelerate electron. So whatever is the physical process according to which X-rays are coming out. So what should be the lowest wavelength when the potential difference is 195 keV? So for that, we use this law, which is called Duane-Hunt law, which relates the minimum wavelength to the accelerating voltage. So basically, lambda is hc by E times V, where h is the Planck's constant, which is 6.626 into 10 raised to the minus 34 joules per second. C is the velocity of light, which is 3.00 into 10 raised to the 8 meters per second. E is the electronic charge, which is 1.602 into 10 raised to the power 90 minus 19 coulomb. And V is the voltage, the accelerating voltage, which is 195 into 10 raised to the power 3 volt. Plugging all these factors together, we get lambda minimum is 6.36 into 10 raised to the minus 12 meter. Then we take another problem. Now in this problem, simultaneously conserving energy and momentum, calculate the energy of the neutron emitted in the forward direction by a beam of 150 keV neutron undergoing the DT reaction in the tritium target. So we were talking about DT reaction in the earlier presentation. In that DT reaction, an alpha particle, a neutron, and some energy is produced. And the Q value of this reaction is 17.6 MeV in the center of mass frame. So what this problem wants is, what is the energy of the neutron emitted in the forward direction? So step one is when we talk about the particle masses. So the neutron has got a mass which is 1875.6 MeV per c square. Triton has a mass 2808.9 MeV per c square. Alpha particle has a mass 3727.4 MeV by c square, and neutron has a mass of 939.6 MeV by c square. Then in step 2, we calculate the center of mass energy contribution from neutron. So basically the initial energy is through neutron, which is the center of mass energy of the neutron. Now the energy of the neutron in the lab frame is 150 keV. So in the center of mass frame, it is equal to mass of the triton divided of mass of the neutron plus mass of the triton into the energy of deuteron in the lab frame. So we plug in all these quantities. 2.2808.9 is the mass of the triton, and 1878.6 MeV by C square is the mass of the deuteron. And so we plug in all these quantities to get the energy of the center of mass frame, and that is equal to 89.85 keV. Then in the step 3, we talk about the total energy available in the center of mass frame. So after reaction, Q amount of energy is released, and initially the energy that was spared, extra energy, was the center of mass energy before the reaction. So the total available energy is Q plus ECM. So it is equal to 17.6 MeV, which is the Q value, plus 0.08985 MeV. So that is the available energy, which is equal to 17.68985 MeV. Now this is the energy. Now this energy is going to be distributed between the alpha particle and the neutron. So the final state kinematics in the center of mass energy is shared between the neutron and the alpha particle in the CM frame. So the neutron will share this much amount of energy, which is m alpha over m neutron plus m alpha into the E available. So m alpha is given to you, and so is m neutron. So you plug in those values to get the available energy for the neutron in the center of mass frame, and it turns out to be equal to 14.1 MeV. Now in the final step, we convert the center of mass energy for the neutron into the lab frame. So that can be done simply by talking about the boost that the neutron gets from the deuteron motion. So in the center of mass frame, the deuteron is having some energy. Now that energy is basically in the lab frame is equal to 150 keV. So the energy of the neutron in the center of mass frame will get a boost from the deuteron motion, and then the total energy will be the energy in the center of mass frame for the neutron plus the energy of the deuteron, which is very small compared to the energy of the neutron. So finally it will get 14.25 MeV. So the forward energy of the neutron in the lab frame is 14.25 MeV.